Whenever we think about this place, or whenever I think about this place, I'm always reminded of Faraday, the great Michael Faraday. And I think he's really an inspiration. And I think he'd be an inspiration for sort of young people getting into science today, because as we all know, he didn't come from a very privileged background. And it was at a time where people were very prejudiced against him for that. The scientific community was very prejudiced against him for that. But he triumphed. We all know what a great, great physicist he was and an inspiration to generations that followed. So I'm here today to talk about some fantastic numbers. But more than that, I'm here really to talk about the fantastic physics that emerges from those fantastic numbers. So I think for me, that's how numbers really come to life. It's not enough for a number just to be a number. You need to give it personality. You need to give it some spirit. And for me, the place that numbers get that personality and spirit, the place that brings them alive is physics. When you try to squeeze numbers into our physical world and think what they might mean. And that's really what this talk and what my book is all about. So here's another book. This is, you can see it's a bit of a knackered old Collins English dictionary. This was a present I got off my mum and dad's, I don't know, ages ago, when I was a kid, basically. And when they gave me this, I was like, why have you got me a dictionary? Because, I've not really been that interested in words. Not really what you should say when you've written a book, right? But, anyway, so I wasn't really that into words. I was like, well, why have you got me a dictionary? All I really cared about was basically maths and numbers and Liverpool Football Club. So, anyway, I looked at the dictionary. I thought, okay, well, it hasn't got Kenny Dalglish in it or John Barnes. Okay, so I'll just look up some numbers then. So I did. So I started looking up, a trillion. I like big numbers, so it's like a trillion. All right, okay, maybe a quadrillion, and then I could see the pattern emerging. So I'm like a quintillion, and I carried on like this until I reached a centillion, which is a 1 with 600 zeros. That's at least in the old British number system, which is obviously the best one. And so that was as far as I got. And I was pretty excited by that. But what I didn't find in this book, and which would have really excited me at the time, were numbers like a googol and a googolplex and Graham's number. Really, truly gargantuan, truly fantastic numbers. And what would have excited me even more is the fantastic physics that you can emerge from those numbers. So we're going to start off with big numbers in this talk. And I'm going to ask you a question. What is the biggest number you can think of? So does anybody want to shout out one of those numbers? Big number, just any big number. Yeah, go ahead. Oh, very good. That's one of the infinities. Okay. 73 is not very big. Anybody else? Yeah? 3, very good. Okay. 40, is that 42? Yeah, it's bigger than 41. Anybody else? Got any more? Yeah? Right. So we have had infinity. I thought somebody would, I know somebody did sort of say infinity, but I thought somebody would say infinity because, well, I'm not going to talk about infinity. Infinity is not really a number. It's also lots of numbers, one of those weird ones. It's not a number and yet lots of numbers at the same time. I want to focus on finite numbers and big finite numbers. Now, somebody's already mentioned 3. I'm not going to talk about 3 today. I'm going to talk about some other big numbers, which are just as cool. So let me start with this one. It's worth $1 million, guys. Do you know the answer? Yeah, go on. What's the answer? It is a googol, right? And you didn't even cheat. This guy cheated, right? You had a guy coughing in the audience. Tequin Whittet. What kind of a name is that? Tequin Whittet was coughing in the audience and telling him the answer. He got it. He got his £1 million and then he got it taken away. It's unfortunate for him. But yeah, the answer is googol. Well said. It is 1 followed by 100 zeros. Clearly, that's a very big number, as we can all agree. Look how big it is. Wow. Okay, that's a big number. It's fun to imagine a googol. It's sort of like, never mind who wants to be a millionaire. What about who wants to be a Googleaire? What are you going to do with a googol pounds? Right? Well, you could buy every particle you can literally buy everything. You could buy every particle in the universe and still pay billions and billions and billions for each one. So literally, Google's way bigger than the number of particles in the universe. You could probably just about afford Kylian Mbappe's wages with a Google pounds. Just about. So where does the Google originate from? Well, it originates from these two guys. So this guy here on the right-hand side, that's Edward Kasner. He was a famous physicist at Columbia University in New York. And I mean, he's famous because he has a space-time named after him. That's, it's a sort of goal of every physicist to have a space-time named after you. He has his own space-time named after him, so he's clearly made it. The space-time he has, it's a weird one. It's people talk about it in the context of sort of the early universe, the Big Bang, and it's like it sort of stretches in one direction and squashed in another. Anyway, we're not here to talk about his universe. We're here to talk about this number. And what Kasner was doing when he was thinking about Google, he was actually writing a popular science book. So we're in good company. And he wanted to convey how big infinity was. And so he wanted to get some big numbers, big by anybody's standards, a number like 1 followed by 100 zeros. And he wanted to say, Rich, essentially, this is nothing compared to the infinite. But he needed a name for this big number. So he consulted his nephew. Now, that's Milton Sirota, Kasner's nephew. He was 9 years old at the time. He's clearly not 9 in that picture. I couldn't find a picture of 9-year-old Kasner, 9-year-old Milton. He died only very recently, actually. Anyway, so he consulted his nephew, 9 years old. I need a name for this big number, 1 followed by 100 zeros. And then in a stroke of genius, Milton came up with the word Google. And that obviously later on in life led to various lawsuits and so on and so forth, as you can probably imagine. Anyway, so this was, but he didn't want to stop there. Kasner wanted to go on and build even bigger numbers. So he said, right, I need a number that's way bigger than a Google, because I really want to show how you sort of step towards infinity. So I need an even bigger number. Well, I'm going to call that a googolplex. I need another number which is going to make a Google seem really small. So I'm going to call it a googolplex. So he said to Milton, okay, this number makes a Google seem really small. So what number should I choose? I'm going to call it a googolplex, but what number should I choose? So Milton says, well, a 1 followed by zeros until you get tired, which is not very precise. I mean, mathematicians like to be a bit more precise than that. But that was the suggestion Milton came up with. So I decided to think a little bit more about this, try to figure out how big that number would actually be. So this person here on the left-hand side, his name is Randy Gardner. And he was a teenager in the 1960s, and he took part in some sleep deprivation experiments. That's what they did. They experimented on teenagers in the 1960s in America. But anyway, so he took part in these sleep deprivation experiments, and they kept him awake for 11 days and I think 25 minutes. So pretty hard going. Anyway, so I decided to figure out, well, if he'd spent the whole time writing zeros, how many zeros would I reckon he'd have written? And I reckon at a fairly conservative estimate, assuming he wasn't writing like crazy, he'd have written about 2 million zeros in that time. And that's still not very precise, though. So maybe a googolplex is a 1 followed by 2 million zeros, but it's not very precise, is it? So certainly Kasner wanted something a little bit more precise. So he decided to come up with a number which was even more gargantuan. And he actually went for a 1 followed by a googol zeros. So a googol, remember, was a 1 followed by 100 zeros. A googolplex is a 1 followed by a googol zeros. This is truly enormous. But you don't have to stop there. In maths, we can always take it up another level. Okay, so a googolplex is a 1 followed by googol zeros. So let's have another one, a Google duplex. Well, that's a 1 followed by a googolplex zeros. Now, this is just getting silly now, right? This is getting off the scale. But we don't stop. We go to a Google triplex, which is a 1 followed by a Google duplex zeros. And then we go to a Google quadruplex, which is a 1 followed by a Google triplex zeros. And you can carry on like this. And you can see you're rapidly going to get to really, really big and gargantuan numbers this way. And this uses a mathematical method called recursion, which is really powerful. And we'll see it again later on in the talk. But I think a googolplex is already a big enough number for us to really start to see some big physics. So to really see how big a googolplex is, to give it the personality it deserves, I want you to imagine the googolplexian universe. So what is the googolplexian universe? Well, it's a universe which is a googolplex across in meters or inches or whatever Earth-like units you choose to use. It doesn't really make a lot of difference. So imagine a universe that if you literally want to circumnavigate it, you have to go a googolplex meters. Now you might ask, is that our universe? And the truth is, it might be our universe. We don't know. The observable universe certainly doesn't extend this far, but we don't reach the edge of the observable universe and hit a brick wall. It carries on. It certainly carries on. And it's certainly possible, it may even be plausible in some theories of the early universe, to have a universe that is truly this big, a googolplex meters across. And so as soon as you realize that, you can really start to imagine some pretty funky physics. So here's me in the googolplexian universe. There you go, there I am, looking a bit younger there. I'm near Earth. I seem to be, it's not to scale this, just to be clear. I'm not a giant. Anyway, so that's me near Earth. Okay, now if I lived in a googolplexian universe, then something remarkable would be true. That very, very distantly in this universe, you would find my doppelganger. Why are you laughing? Are you saying you just don't believe in the idea that this could possibly, that there's doppelgangers, or you don't think that's my doppelganger? It's a bit harsh. Okay, what if I said that this was my doppelganger? Now you're thinking that's more plausible, aren't you? Yeah, whatever. Right, anyway, okay. I'm actually talking about an exact doppelganger. A genuine, exact copy, right down to the quantum DNA. Same nose, same eyes, even the same thoughts about Mo Salah signing a new contract and how happy I am about that and all those sorts of things. Okay, so this really is an exact copy. Now it seems crazy, right? But in a googolplexian universe, the odds are the doppelgangers will exist. My doppelganger, your doppelganger, and not only that, many times over. A googolplexian universe is so large that the odds are overwhelmed emphatically. As I said, it's not just me, it's not just you, it's also, I'm sorry to say, James Corden. He will also have doppelgangers. Piers Morgan will have a doppelganger. Donald Trump. Oh, it's really quite upsetting when you think about it. Okay, so I'm going to come back later on in the talk and explain why this is. But for now, I want to sort of ramp things up a little bit and think of another big number, even bigger than a googolplex. It makes a googolplex seem absolutely minuscule. And that is Graham's number. Graham's number is very, very scary. It's truly enormous. It's so big, it's terrifying. Why is it so terrifying? Now, I assume some of you might already know. Graham's number, so let's go back to where Graham's number originated from. Well, it was named after this guy, Ron Graham, another mathematician who died fairly recently. As you can see, Ron Graham was not a conventional mathematician. He was, you can see him juggling. That's not a fake picture, that's real. Okay, he could juggle a lot of balls. He actually used to be in a circus. I think there's Science Circus here tomorrow night, actually. Ron Graham would have fitted in perfectly at that. So yeah, he used to, as well as being a great mathematician, he performed in a circus. Apparently, you'd be in an office with him talking about maths, and in a moment, he would suddenly just start juggling, or he'd jump about on a pogo stick, or he'd do a headstand or something, right? So he was really unconventional guy, but also a great mathematician. And the reason this number bears his name is because, well, it's quite a famous number. It actually appeared in the Guinness Book of World Records as the largest number ever to appear in a mathematical proof. Although the funny thing is, that's not even true. It never actually happened. The number that we now call Graham's number is not a number that appeared in Graham's proof. It was a number that Graham had come up with. It's very similar to the number he'd used, but it was easier to describe, and he was using it for a popular science article. So, how can we describe Graham's number. Now, it's very dangerous, as we'll see in a minute, to think about Graham's number in the usual way of thinking about numbers, digits. Don't do that with Graham's number. We'll see why in a moment. But you can think about it in another way, and that's using Knuth's arrows, named after Donald Knuth, who's a computer scientist from Stanford, I believe. So we need to sort of introduce this idea sort of bit by bit. So to understand Knuth's arrows, let's start with the idea of what multiplication is. Let's really think about fundamentally, what is multiplication? Well, multiplication is just repeated addition. That's what it is. Okay, so when you say 3 times 3, you really mean 3 added to itself 3 times. 3 times 4 is 3 added to itself 4 times, right? It's repeated addition. Okay, so that's fairly simple. So if you've got repeated multiplication as repeated addition, what's repeated multiplication then? Well, that's exponentiation. Okay, so when you say you've got 3 multiplied by itself 3 times, you say that's 3 to the power 3, right? T'others, my wife calls them. So 3 to the power 3, or 3 to the power 4, that's 3 multiplied by itself 4 times. It's repeated multiplication. And you know that with exponentiation, you can get to bigger numbers faster. But Knuth really wants to build on this idea. So he introduces a new notation for this. So he says, instead of saying 3 to the 3, I'm going to say 3 arrow 3. That's the notation he introduced. And we'll see why now, because now he's going to build up even further. You've got repeated addition gives multiplication. Repeated multiplication gives exponentiation. What's repeated exponentiation give you? Well, it gives you something called tetration. And Knuth would use it with a double arrow. So 3 double arrow 3 means 3 arrow 3 arrow 3, where you've got 3 groups of them. Okay? So in other words, that means 3 to the 3 to the 3, which is 7.6 billion. So this double arrow, this idea of tetration, repeated exponentiation, repeating your t'others, right? You get very big numbers very quickly. But Knuth doesn't stop there. If you can do double arrows, you can do triple arrows, right? It's just repeated double arrows. So you can have 3 triple arrow 3, but that's just a repetition of the double arrows. So that's really 3 double arrow 3 double arrow 3, which is 3 double arrow to the 7.6 billion, which is 3 to the 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 3, where the tower of threes is 7.6 billion levels high. So it's truly enormous. If each of those sort of threes were about 2 centimeters in height, that tower of threes would reach all the way to the sun. It's a truly enormous number, and we've just done it with the simple triple arrow. It's sometimes called the sun tower, this number. But we are nowhere near Graham's number. We are nowhere near it. If we can do triple arrows, well, we can do quadruple arrows. Okay, well, what's quadruple arrows? Well, that's repeated triple arrows, right? I'm not going to go through it again. Just take my word for it that this is ginormous. Okay? I'm going to call it G1. Now, here is the point where we're really going to turn on the boosters. Right? Up until now, we've been adding an arrow each time, and that repeats what's gone, that allows us to do repetitions of what's gone before, right? And that allowed us to get sort of really, really big, really quite quickly. But now we're turning on the boosters. So now the number of arrows is going to grow really fast. Up until now, it's been growing by 1, but now we're going to grow the number of arrows really fast. So in the next step, we're going to have G1 arrows. So the number that we got before is now going to dictate the number of arrows. Remember, each arrow, addition of each arrow takes you to a new level of generating numbers. Now we're growing the number of arrows massively. We're truly gargantuan. This isn't just ginormous. This new number now, this G2, is frankly silly. But we don't stop there. We're nowhere near Graham's number. I mean, these are just off-the-scale numbers now, but let's carry on. G3. We now use G2 to tell us how many arrows there are. Well, this number is not just silly. This is a whole new level of silly. This is Donald Trump silly. It's just a whole new scale of silly. Still nowhere near Graham's number. We've got to go to G4. Each time growing the number of arrows enormously, G5, G6, G7, G8, G9, G10, and so on and so forth. And we carry on like this until we get to G64, just truly, just off the scale, enormous number, and that is Graham's number. Okay, it's just gone beyond anything you can possibly hope to imagine. But imagine it, we'll try, okay? But that will be the death of us. Because when you think about Graham's number, this is what happens. Black hole head death. Now try saying that when you're reading a book on the audiobook. It's quite difficult, it's quite a mouthful. Okay, so black hole head death, what is that? Well, that's what you get when you think about Graham's number the wrong way. So don't think about Graham's number the wrong way, because you do not want to get black hole head death. Okay, so what am I talking about? Let me take you back to Pompeii and Mount Vesuvius and the eruption of 79 AD. You all know it, you all know the story. You've all seen the images of the victims of that eruption. You know, they were encased in ash and sort of immortalized in time. But I don't want to think about what happened in Pompeii. I want to think about what happened in the nearby cities of Herculaneum and Oplontis. Because there, they died a very different death. So here are the people in Herculaneum and Oplontis, and when the volcano erupted, this is what happened to them. Literally, their heads exploded. This is true. There were fragments of skulls, skull fractures, found in and around that area from when the eruption happened, which showed evidence that the fluids on their brain had boiled and their heads had exploded. It's truly horrific, but it's nothing compared to black hole head death. So black hole, this is me about to suffer from black hole head death. Black hole head death is what happens when you think about Graham's number. So let's see it. So you're picturing Graham's number in your head, digit by digit. The digits are filling your brain, and bang, your head collapses to form a black hole. Chances are you wouldn't even get that far. Chances are the black hole the heat would rise inside, and your head would want to explode. But if you could stop it from exploding, at some point, inevitably, your head would have no option but to become a black hole. Question is why? Well, let's see. So this is where we need to bring in entropy in the game, which probably you've started to notice that there's a bit of entropy floating around here, right? So entropy is, people often talk about what entropy is, and they say, oh, well, it's a measure of disorder, right? Entropy is a measure of disorder. A disordered system, like, I don't know, an untidy bedroom, has more entropy than an ordered system, like a tidy bedroom. And that's kind of true, but it's a little bit loose. So I want to be a little bit more precise about what entropy really is. But I need 3 volunteers from the audience to help me at this point. So do I have 3 volunteers? Yep, you going to come over to the front? Yeah, go ahead. And yeah, do you want to come in? Thanks. Okay, so what's your name? Jack. Jack? Rebecca, I think I know your dad. And Samuel. Right, come to the front. Okay, so if you just stand here a second, and we'll be using you in a moment. So notice you've got these entropies written out. Now you'll notice that this is my one, right? Now, what I want you to think about is I want you to look at these ones down here. Now it's clear that, Jack, which one of these entropies matches my one? Yeah, and it's only that one, right? You agree?
I think, yeah.
You sure? You're looking a bit unsure there. No, clearly, this is the only one that matches my entropy, right? So this is the only other state, I'm not talking slight physics language, this is the only other state that matches my state. This one doesn't match, and this one doesn't match. These appear to be in different states. And we can tell the difference by looking at them, right? We can measure that. Okay, so now what I'm going to do, and this is where I need you guys to join in, I want each of you to sort of stand by one of the sets of letters and by one of the buckets, and I want you to start grabbing them and put them in your bin. Go on. Nice and quick. It's a very enthusiastic destruction, I love it. Okay, guys. Right, now at this point, I really wanted to set them on fire. This is really what I wanted to do at this point, but I really didn't want to fill in a risk assessment or anything like that. So I'm going to do something slightly different. So guys, here's what you got to do. Pick up the buckets, or bins, I suppose what they are, right? And when the music starts, I need you to go into the audience and run around and start passing the buckets around, passing the bins around, and then whoever you pass it to needs to pass it on to somebody else. And then I just want these bins to sort of move all around, high speed around the lecture theatre before they get brought back at the end. Okay, you ready? Okay, when the music starts, ready, steady, go. I need you running, guys. Get out your seats. Oh no, he's dropped it. Move it across. Move it around the room, guys. Around the room. You stayed in one section, move it across. Go on, guys, intervene. Get it moving more. All right, are we done? Do you guys want to get them back from the guys in the audience? Thank you. Put them at the front. You want to put them down there at the front? Well done, Jack. Okay, just put them at the front. Okay, guys. Okay, so what's your name again? Samuel, which bucket? Remember, only one of those buckets, only one of the contents match mine, right? Which one was it?
Have to take all of them out individually to find out.
No, you're not allowed to look inside.
Can I help?
I don't know.
Do you know?
Maybe the middle one?
Why?
It looks... Because he was like doing his really slowly and they were all...
Well, that wasn't supposed to happen. We're going to have to do this again, are we?
It's not mine, because I packed them really fast, and that looks like it's been packed really fast, so it's not this one.
You lot are too clever, right? You need to go and sit down. All right, thanks, guys. You're not as clever as these guys. You would probably say it's pretty hard to tell, right? I would say impossible to tell just by looking. We know one of them matches my bucket, but it's impossible to tell, right? Just by looking at it, it's impossible to tell. So they're all in different states, but they could all correspond to this. And that's what entropy is. We've kind of lost some information. Entropy is a measure of missing information. And we've lost information. By creating this disorder, we've lost information. There are now 3 possible states that could just as well describe this. We cannot tell. Based on the sort of macroscopic data that we have available to us, the experiments that we can do just by looking, it could be any of these 3. And statistically, we say it could be all of them. We average over it. And that missing information that we seem to have lost, that's what entropy is. It counts the number of ways you could get the same thing, the number of states that could give you the same macroscopic object. You just don't have access to that information. Now, you could dive into it, as I think one of you wanted to do. Dive in and actually figure it out. Okay, but maybe that experiment's not practical to you. Maybe it's not even possible, because there might be black holes floating around and they really like to hide stuff, okay? But that's what entropy is. It counts the missing information, okay? So something in the system has hidden that information from you, and there's now many possible ways you could get the same thing as far as you can tell. They're all potentially equally good descriptions. You cannot tell which one it actually is, and that gives it entropy. Okay, so how do you measure entropy? Well, it's missing information. So information is measured in bits. So when we think about that, we can think about, a coin toss, for example. So you toss a coin, it can be heads or tails. That's 2 possible outcomes. And so we say that's 1 bit of information. If you have two coins, then you can have 4 possible outcomes, right? Heads, 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 tails, tails, heads, or tails, tails. And that gives you 2 bits of information. If you've got 3 coins, then the number of outcomes grows exponentially. You have 8 possible outcomes, 3 bits of information. If you go to a Google coins, you'll have 2 to the Google sort of outcomes and a Google bits of information. That's how we measure entropy. And all macroscopic objects have entropy, including dinosaurs. Right? Dinosaurs have entropy. Why? Because there's missing information. We look at that dinosaur and we think, right, well, I can tell it's a dinosaur. I can tell it's a stegosaurus, right? I can sort of measure its temperature. I can measure its mass. There's lots I can tell about it. What I can't tell is what the electron inside its small intestine is doing. It could be spinning this way. It could be spinning that way. I can't tell. It's missing information. There could be a state of that dinosaur where the electron's spinning up and another state where it's spinning down. I don't know. I can't tell. So they're different possibilities. They're different possible states that could describe that stegosaurus. And they all add up and contribute to its entropy. So the more missing information you have, the more entropy. And so it stands to reason that when you have a baby dinosaur who's nice and little, he'll have less entropy than his mummy, right? Because his mummy's bigger. You make an object bigger, it tends to have more entropy, right? Just because there's more capacity for hiding information. There's more atoms and there's more stuff that you could potentially not know about. So when you make things bigger, you tend to increase their entropy. Okay, but you cannot just carry on increasing entropy ad infinitum. For a given size, you cannot just keep feeding information. I cannot just keep increasing the entropy inside this. I can't do it indefinitely. And the reason is because in nature we have an entropic champion. And that entropic champion, that brilliant hider of information, is a black hole. Black holes are the entropic champions in nature. Okay, now why? Why are black holes so good at hiding information? So I'm going to need another 2 volunteers at this point. So who wants to come forward? You don't have to run about this time. Yeah, go on. You want to come forward? And one more. I need one other person. So I can't. Yeah, go on. So one of you is going to be a black hole. So, okay. So this is what's happened, right? So do you want to be the black hole? Yeah, you're going to be the black hole, right? Okay, you stand over there. Now, you're just sort of, you get up one morning, right, and you just brush your teeth, all that. You have a look out the window, and somebody's gone and put a black hole in your garden, right? This is an invisibility cloak, by the way, which is clearly that's how you make invisibility cloaks with black holes. Okay, you need to be invisible, come on. So this black hole's appeared in your garden, right? Slightly alarming, because it's not a very big black hole, and smaller black holes the more dangerous they are, actually. It's the small ones you have to worry about, because you're closer to the singularity where the sort of, the gravitational forces become infinite. So you don't want to go near a small black hole. Big ones are fine. Small ones, bad. Anyway, so there's a small black hole in your garden, which is bad, right? Anyway, so what's going to happen is you go about your daily business, you tell everybody about the black hole that's appeared in your garden, right? Then you go to bed that night, okay? And the next morning you wake up. Now, something's going to happen. You have to turn away at this point. Okay, turn away. Now, the black hole is going to swallow, well, I'll tell you what's going to happen. I'll show you. The black hole is going to swallow an elephant, or it might swallow a dinosaur. Okay? We don't know. But the important thing is, when we look at this black hole, there's only certain things that we can measure about it. We can measure its mass. Now, I was going to bring some scales, but I thought that'd be a bit impolite to start weighing the audience. But anyway, so we can measure a black hole mass, we can measure its charge, and we can measure its spin. Okay, do you want to spin around? Are you spinning black hole? Yeah, there he is, spinning away. Okay, so black holes, that's the only things we can measure about the mass, charge, and spin, nothing else, right? We can't. The black holes hide everything else. So you can't do anything else but measure those things. But we're going to say you're able to measure those things. But overnight, our black hole is going to swallow one of these guys, right? Now, these both have the same mass, as it happens, the elephant and the Triceratops. And yeah, that's it. They've got the same mass, they've got same spin. Yeah, they're both spinning the same. They've been dancing together, and the same electric charge. Yeah. Okay. Now, overnight, he's going to swallow one. So you have to close your eyes. Close your eyes. You tell me if he's looking, right? Okay, so which one are you going to swallow? Don't say. Okay, hide it. Hide it, hide it, hide it. Okay, right. 1 second, you can look in a minute. Okay, right. Wake up, it's breakfast time, right? Oh, the black hole's still in your garden, mate. It's got a bit bigger. I think it's got a bit bigger. Yeah? What do you think it's done? I don't see the elephant, but I don't see the triceratops either, because you had an elephant and triceratops in your garden, by the way. I don't know if you... that's a bit weird. But anyway, so you've got these creatures in your garden, but they're both gone now. But he's what are you going to do? Which one's he swallowed?
You wouldn't know.
You couldn't... So you're going to guess?
No.
Very conservative.
Triceratops.
You reckon he swallowed the triceratops? Are you going to? So you're going to bet? You want to bet?
No.
Well, you don't want to bet.
No.
You're prepared to put any money on it at all.
No.
Not even £1.
No.
Really?
Yes.
That's very conservative. I mean, I thought I was going to have to go to like all your life savings and like everybody else's life savings in the room. Okay, but you're prepared because and there's a good reason. He's a clever boy, right? There's no way for him to know, right? Because the only thing he can measure is the mass, the charge, and the angular momentum, right? And the spin. And it was the same for both objects. So it's impossible to tell. Black holes have hidden this information, and they are brilliant at hiding this information. Now, the information will come out eventually through Hawking radiation. This is when you apply quantum mechanics to a black hole, and it gives off radiation. And we do believe that somehow, although we don't know how, the information of what he swallowed will be in that radiation. We just don't know how it's stored. It does seem that the black holes are amazing at hiding information. That's why they're the entropic champion. So do you want to tell him which it was? There's Hawking radiation comes out, and if it's all scrambled, but it was the triceratops. You were right, you should have bet. All right, thanks, guys. So black holes really are the entropic champion. Nothing can hide information better than them. Okay, so let's bring us back to thinking about Graham's number. Okay, now Graham's number, truly gargantuan number. There's a lot of information in it. It's got numbers in it, and numbers have information. How much? How much information in a number? How much information in a digit? Well, let's think about a single digit. Okay, so one digit has 10 possible outcomes. 0 to 9, right? 10 possibilities. So that's somewhere between 8 and 16. So that means a single number, a single digit, contains between 3 and 4 bits of information. Okay, somewhere between the two. So that's just one digit. Graham's number has a lot of digits, right? It really does have a lot of digits, a truly enormous amount. So each one of them, as it enters your head, if you picture it in your head, you start trying to picture Graham's number, the digits start to appear in your head. Each time a new digit appears, it adds a little bit of information. It starts to hide a little bit more information in your head, between 3 and 4 digits each time. And as you accumulate more and more and more and more and more and more bits, you start to take on mass because that information weighs. You take on more mass, you take on more information. Eventually you get to a point, actually it's going to actually cause eventually it'll start to cause your head to sort of heat up. Right? And it'll want to make your brain boil. But if you can somehow stop your head from exploding, if you can maybe have a reinforced head, say, okay, and you can keep feeding this information, these numbers of Graham, these digits of Graham's number into your head, you're taking on more and more bits each time. You've got a reinforced head now, more and more bits. It wants to get really hot, but you manage to stop that. And eventually you get to a point where there's so much information in the space of your head, so much information hidden, that only the entropic champion could hide that much information in that space. And we know what the entropic champion is. It's a black hole. So it becomes inevitable that your head has to be a black hole at that point. And that's when black hole head death kicks in. There's no other option. There's no alternative. If you try to think about Graham's number like that, the end point will be black hole head death. Now, you're still nowhere near Graham's number, by the way. You're still miles away from Graham's number. This happens way before. You don't even scratch the surface, and you've already got black hole head death. You could carry on if you were like that. Try, maybe get your mates, you're sitting there with a black hole head, and your mates are a bit freaked out because they get too close and they get torn apart by the tides of gravity, so that's not ideal. But they try to carry on feeding more information into your head, so more digits of Graham's number. Well, the only thing that can happen now is the black hole has to grow. And the black hole will grow, keep feeding in more information, black hole grows. Eventually it grows really big, and then your mates actually aren't as freaked out now because big black holes are not as scary, so they can actually give you a kiss at this point, as long as they're running at the speed of light. But keep feeding it. Eventually, this black hole head that you had has to grow bigger than the size of the universe, and you're still barely going to touch Graham's number. That's how big Graham's number really is. Okay, now that might have all seemed really quite terrifying. But it's not as terrifying as the fundamental idea that this is all leading us to. It's a really, truly terrifying idea. And that's that you are all trapped in a hologram. Okay, that literally one of the dimensions of space that you think you experience could potentially just be fake. And these ideas of entropy and black holes are what lead you to that possibility. So what am I talking about? Okay, so let's try and understand this. So I want to think about ordinary objects, like an egg, or a triceratops, or a Collins English Dictionary. Okay, ordinary stuff, right? How do you grow the entropy of ordinary stuff? Well, you just make them bigger. If you double the size of the egg, you will double the entropy. You'll double the amount of information you can hide. If you treble the volume of the egg, you'll treble its entropy. That's how entropy changes with volume. Okay, double the volume, you double the entropy. That's how ordinary stuff behaves, like eggs and triceratops and dictionaries. That's what they do. But what about the entropic champion? What does that do? What does the black hole do? And this is a very different beast. You might think if I double the volume of a black hole, whatever that means, that I double the entropy, but that's not what happens. Black holes do it differently. Okay? To double the entropy of a black hole, you actually have to double the surface area of the black hole, which is a different thing to do. So you double the size of the event horizon. Okay, that's how you double the entropy of a black hole. And that's very different behavior. It seems it's fundamentally a different dimensionality. Okay, ordinary stuff, you have to grow the three-dimensional area to double the entropy. But for black holes, you grow the two-dimensional area. It's different. And the reason it's different is because black holes are fundamentally, they're deeply gravitational objects. They really feel gravity's crushing embrace in a way that eggs and dictionaries and even triceratops do not feel. Okay, black holes are fundamentally gravitational. So they really feel gravity. So this suggests that when you feed gravity into the game, it somehow behaves like a two-dimensional thing compared to ordinary stuff, which sees three dimensions. Something fundamental there. Something weird's happening when you really think about gravity in our world. It seems like the dimensionality wants to drop. How you store information wants to drop one dimension. So this led these guys to make a really remarkable conjecture. It's probably one of the most remarkable pieces of physics of the last 30 years. So this is Leonard Susskind. He's a physicist from Stanford, very charismatic guy. There's Gerard Tufte, who's a Nobel laureate from the Netherlands. And Juan Maldacena, who's an Argentinian physicist, who I would say probably is perhaps the best physicist around today. And these all conjectured the holographic truth. All those and the ideas of others conjectured the holographic truth. So if I think about this in the context of our three-dimensional world, what would the holographic truth mean? It would say the following. It would say that on the one hand, if we want to encode the physics that we see around us, we can think of it in terms of a three-dimensional world with gravity, right? Where things fall. Okay? That's one way to encode the physics, 3 dimensions of space and gravity. But what the holographic conjecture suggests is that there is an equivalent description of exactly the same physics, in which you do not have gravity and you only have 2 dimensions. It's the same physics, the same phenomena, but you don't need 3 dimensions and you don't have gravity. So this is really people find this very difficult to sort of imagine. What do you mean I don't have gravity? What do you mean is that I don't have a dimension? It's an illusion. Think of a hologram. Think of what a hologram really is. A hologram is, when you have a hologram, you have a holographic plate, clearly a 2-dimensional thing, right? You have information stored on a 2-dimensional holographic plate. It's stored in a series of sort of light and dark bands of different density. They're stored on this holographic 2-dimensional plate. There's information on there. Now, that's one way. You can just look at it. You can just decode the information that way. That's what the information is. It's stored on this 2-dimensional holographic plate. But what you can do, you can decode it differently, the same information. You can shine some monochromatic light through the holographic plate, and you can create this 3-dimensional image. That's how holograms work. Now, but that 3-dimensional image only contains the information that was already stored on the plate anyway. So it's not like, it's the same information, right? Just encoded differently. One appears to be in 3 dimensions, one appears in 2. This is working the same way. Same physical phenomena, just encoded 2 different ways. You can think of it in terms of a 3D world with gravity, but exactly the same physical phenomena in a 2D world without gravity. Okay, we just choose, mathematically, if you like, to think of it in terms of the 3D world with gravity. But we could as well just think of it the other way. It's the same phenomena. It's the same phenomena. And is this true of our universe? We don't know that for sure. What we can say is that there are some universes, sort of toy universes, where this is definitely true. The evidence is overwhelming. That you can have one description which involves gravity and sort of a certain number of dimensions, and a completely equivalent description which doesn't have any gravity and has 1 dimension less. You think of it as living on the boundary of that space. Is it true of our universe? We can speculate. I would say it seems to be something that does seem to be fundamental truism of gravity. Okay, so this brings us back to our doppelganger. That's horrific, isn't it? Sorry, guys. So this brings us back to our doppelgangers. Actually, I'm going to show you something even more horrific. Look at that. Doppelgangers. So what has all this got to do with doppelgangers? Right. Well, let's think about James Corden. I'm sorry. We're going to think about James Corden, and we're going to think about the sort of volume of space that he occupies. It's roughly a cubic meter. Okay, and that's one particular state, right? You can think of it as one state principle, one quantum state that's describing James Corden, and it occupies that 3-dimension, that cubic meter of space. Now, a cubic meter of space the quantum state could also describe, a different quantum state, describe a cow. Or it could describe an alien. Or a different quantum state could just describe, empty space, right? A cubic meter of space can be in many different states. So now let's try and figure out how many. Okay, so what we can do is we can take that cubic meter and we can split it up into its fundamental building blocks. Okay, so we take a cubic meter of space, and we're going to break it up into the smallest bits we can imagine. Okay, the smallest bits are a size, the Planck length. That's 10 to the minus 35 meters. It's a tiny distance. It's the fundamental sort of smallest distance in nature. If you try to go any smaller than that, space-time itself starts to break down. It gets overwhelmed by quantum effects. So you can imagine taking your cubic meter of space and sort of breaking it up into these tiny little building blocks, little squares, 10 to the minus 35 meters across. Okay, you can count how many you've got in total. It'll be about 10 to the 105. That's how many of these. Now, we can imagine that each of these little building blocks is in, say, one of 2 states. It's just conservatively. It's either black or it's white. And you can think about how many different patterns you could sort of create, how many different patterns you can make out of these guys. Well, each block is either black or white, so that's 2 possibilities. The total number of patterns you can imagine is 2 to the 10 to the 105. That's bigger than a googolplex. Okay, so you might imagine there are 2 to the 10 to the 105 possible quantum states that can describe a cubic meter of space. And that's bigger than a googolplex. It's also wrong. right? Because gravity comes into the game. And gravity tells us this isn't how you should count information. Remember, gravity wants to make things sort of two-dimensional. It wants you to think about the surface that surrounds this space. That's where it wants to encode the quantum information. So you should really be putting your building blocks on the surface of this cubic meter of space. Well, how many building blocks can you put on that? Well, it's not 10 to the 105, it's 10 to the 70 now. It's a smaller number. And so the number of patterns is 2 to the 10 to the 70. So what's happened here is gravity, some of those patterns you had in the first estimate are just forbidden. Gravity forbids them, essentially because black holes want to start forming. It just stops them from happening. Okay. So it's actually fewer. Now this new number is less than a googolplex, and that's crucial because now we can think about James Corden again, right? So we imagine this cubic, so he's James Corden, right? And he's occupying this cubic meter of space. He's one of 2 to the 10 to the 70 patterns. Okay, quantum states. Now the space next to him, it's very unlikely he stood next to his doppelganger. It's very, very unlikely. So this bit of space next to him is another one of those 2 to the 10 to the 70 quantum states. And then this space next to him is another one of those 2 to the 10 to the 70 quantum states, and so on. And you can carry on going like this, sampling every single cubic meter of space. And you can imagine doing this, not practically, but in principle, and reaching all the way across the googolplexian universe. Now, 2 to the 10 to the 70 is less than a googolplex. Okay? In fact, it's a lot less than a googolplex, a lot less. So eventually, you're going to start seeing repetitions. Now, there could be repetitions of empty space. Probably most likely you'll see them first. Just empty space. Oh, there's more empty space. Another one that's in the quantum state of empty space. Oh, another one that's in the quantum state in empty space. You start to see repetitions. And maybe a repetition of James Corden initially is quite unlikely. But a googolplex is so much bigger than 2 to the 10 to the 70. You overwhelm the odds, and it becomes almost inevitable that James Corden will have doppelgangers. Sorry. So, I'm going to change gears now, just before the end. We've been talking about big numbers. And, you know, there's big physics with big numbers. But there's also little numbers. And little numbers, well, you can have, it's not little physics, you can still have big physics. What you can have with little numbers is unexpected physics. That's what little numbers give you. Little numbers in nature tell us that something in the universe is unexpected. Let me explain why. So this is a score that I got on a sort of musical test that was doing the rounds at the weekend. I don't know if anybody else saw it. I know my niece saw it because she did it. This is not a very good score. This is a bad score. This is my score. I am not very musical, as you can tell. I am a terrible singer. I did think at this point of actually singing, but you'd have been scratching your ears out. It'd been awful. People have been running out, right? So I'm not going to sing, but you can see here that I am not very good at music, right? This is terrible. So my niece actually got a better score, but not much better, actually. And So you can see that the vast majority of the population would be better than me at this, at music, at singing. So because of this, I think we can all agree it would be quite unexpected if I were to win the X Factor. This would not be an expected thing. The probability of it happening is a very, very small number, right? A very small number. And you see that small numbers connect to the unexpected. The chances of me winning the X Factor are very low. But whilst that might seem like very unlikely, it's nowhere near as unlikely and unexpected as our universe. Because our universe is described by a really small number, the smallest number in nature, 10 to the minus 120. Okay, this is a truly tiny number. It is the smallest, so there's 119 zeros there after the decimal point, and then a 1. This is the number that describes how unexpected our universe is. It tells us about the weight of the universe. So when you think about how much does the universe weigh, I'm not interested in the stars and the planets. I'm interested in the weight of empty space itself, the mass of empty space. So take all the stars and planets out of the universe and ask how much is the stuff that's left over, the empty space that's left over, how much does that weigh? You might say nothing. It's just empty space, right? But that's not true. Empty space is a really exciting place. It's, due to quantum mechanics, it's a bubbling broth of virtual particles popping in and out of existence. And those virtual particles give the vacuum some weight. And actually, we see the effect of that weight on the cosmic acceleration of our universe. Our universe is expanding at an accelerated rate. And we believe it's due to this energy stored in the vacuum of empty space. The problem is, it's very unexpected. Because when we calculate how big the vacuum energy of empty space should be, when we actually use our best theories to calculate and estimate how much energy should be stored in empty space, it turns out that literally just a coffee cup of empty space should have enough energy to blow up every single planet in the observable universe many, many times over. And that much energy will literally crush the universe into oblivion within a moment of being born. So that's not what we see. It's what we calculate, that we expect to see, but we don't see it. Thankfully, the vacuum energy of the universe is really small. We measure it to be really small. It's 10 to the minus 120 times smaller than what our calculations predict it should be. It's the most embarrassing mismatch in physics. It's something that we really don't understand. Some people have argued that the reason the vacuum energy of the universe is so small is because we're here to see it. Okay, they say that, if the vacuum energy has been as large as you expected it to be, then the universe would have crushed itself from the moment it was born, and planets and stars would never have formed, and complex life would never have evolved to then start measuring these things. So in some sense, our very existence is related to the idea that the vacuum energy is small. Because if it wasn't, we wouldn't be here to measure it. Now that might answer the why the vacuum energy is small, is this tiny number. But it doesn't really give us the how. And understanding the how, I think, is probably one of the most sort of important problems in theoretical physics today. It's the problem I've spent my entire career thinking about. And it's called the cosmological constant problem. And I think once it's solved, if that happens in my lifetime, then I think it's fair to say it would be a paradigm shift in our understanding of how the universe works. So, there are many numbers in my book. We've talked about some of the big numbers. There are other big numbers like tree 3, which was mentioned earlier. We've talked about one of the little numbers that tell us about the unexpected universe. And we even mentioned infinity earlier on. But in the interest of this talk not going on for an infinite amount of time, I think I will stop there. Thank you.